Before starting a session, if anyone have any questions, they can type in chat window. We will try to cover it in our session. Dr. Sharma sir has arrived. Welcome, sir. Thanks for joining this session. Sharma sir, are you there?
Hello.
Hello, yes.
I am not able
It's a presentation or something. It's a presentation.
to. So
Yes,
we will
sir.
start at 3:30.
Are you saying anything, sir?
Hello.
Yes, sir. Yes, sir.
Okay. So the other panelists are connected now.
Sir, your voice is not coming properly. If you can come closer to mic, then it will be better.
Voice. No voice in background. Hello.
Yes, sir.
Voice is clear.
Now it is clear. Yes.
Okay. Okay.
Welcome, sir. Thanks for coming with us. Thanks.
So you are Mr. Nirav.
What you are saying, sir?
Your good name?
My name is Nirav Nagadiya.
Okay. Okay.
Yeah.
You know the
Yes, yes.
What about you? Nirav,
Yes, yes, sir. Tell me.
how is the voice now?
What?
Voice heavy. How is the voice?
Your voice is not clear, sir. Many
Am I
disturbances.
audible?
Hello?
Okay.
Whose voice also? Just say when it's resonating.
But your voice is also coming disturbed. Breaking voice is coming.
Many disturbance are there in voice.
Multiple disturbances.
Nirav, now I have changed the position.
Now it is better. Thank you.
Okay.
Okay, thanks a lot.
Okay.
फिर वापस मामला ऑन हो जाएगा। पर अभी कुछ बात करना, अब इस पे क्या करता है?
बात करते हैं।
किससे? नीरव से क्या बात करनी है आपको अभी?
Nirav, why don't you? Nirav,
Yes, sir. Tell me.
can you open your video?
What you are saying?
I am not able to see you. Your presentation is visible.
Yeah, actually, we all are means we also requesting everyone to switch off their camera. Only panelists we are requesting to switch on camera because there will be connectivity issue.
Okay, okay.
Nirav, it is probably better that everyone can be visible right now. And when the webinar starts, then we can switch off the cameras.
Sure.
But at least voice, we should test out the voice for Amita and for Claude and for Sharmaji.
Okay, sure.
I think it is better to put on the cameras for the webinar.
Yes, sure.
Just when we start, we can switch it off in 5 minutes.
Okay, sure.
Dr.
She said something.
Your voice is not coming.
Sharmaji, I think you should try out another camera. Voice is not very clear.
Yeah, your voice is not coming.
Yeah, and now it is good. I think you have to, when you're close to the mic, then it's clear. Otherwise, it resonates for some reason.
I can hear your voice very nicely, but Dr. Amita's voice is not coming.
I don't know why it is resonating. There could be some reason. Nirav Gopal, do you know why? Could you tell me?
Muted.
Now it's okay?
Claude, can you try out your voice?
Nirav, can you hear me now? Well,
Unmuted.
We can hear you.
Yes.
that's fine. First class.
Claude? Claude, can you hear me?
Dr. Amita's voice not coming.
Amita, your voice. No, your voice is not coming, Amita. No.
Really.
Once again,
Hello?
welcome
Can you
everyone.
hear
Yeah. Good afternoon. Welcome.
Amita, can you speak? Amita,
me? Yes.
can you speak? Yeah, this is better.
I'm speaking. Can you hear
Okay.
me?
Now I can hear you. Your voice is coming.
Okay.
So,
So hello everyone.
Hello.
Hi.
Huh? Hi.
So once again, welcome everyone, and thanks for joining us for this wonderful session. My name is Nirav, and I am as a regional manager at Fluidyn, India. Gopal, are you there? Gopal?
Yeah. Yeah. I'm available.
Okay, okay.
Okay, can you hear me?
Yes, yes, it is audible.
Yeah. Okay. Thank you.
So can we start session now? It's almost 3:30.
Yeah, we can start.
Okay. Gopal, please start it with. Gopal,
Yeah.
please start with.
So, 600.
Sir, where is Dr. Mishra?
What you are saying, sir?
Dr. Mishra,
Doctor.
Anthony Mishra.
Yes, yes. Actually, he is busy with some meetings. He will join in mid of the session. He'll try to join.
Okay. Then Mr. Subramanian Neelkantan.
Yeah, he will also join this session.
They will be late.
What, sir?
They will be late.
Yes, yes. We have invited him. He's coming. Gopal. Gopal, are you there? Gopal. Okay. So actually, my colleague has some connectivity issues. So I'm starting with introduction portion. So first of all, we have us as Dr. J.S. Sharma here is here. So for a moderator, we have our expert presenter as Amita Tripathi, Krishna Prasad, and Cloud Sopran. Amita Tripathi will explain you about Fluidyn experience in styrene dispersion and processing and storage. Then Krishna Prasad will explain you about 3D CFD based dispersion simulation and sensor mapping. And Cloud Sopran will try to cover inverse modeling, risk detection, and real time forecast. So I'm not taking much time for introduction, but we'll try to cover little introduction within 2 to 3 minutes. What happened? Gopal, are you there? Okay. So Fluidyn Transport Group firms offer modeling software and also consultancy services in CFD and related area such as the stress analysis, acoustics, heat transfer, magnetohydrodynamics, and CHT, conjugated heat transfer, FSI, fluid structure interaction. And our modeling major area is on environment impact and industrial hazardous simulation. Here we will cover some problem regarding what happened currently in Vizag about styrene leakage. So this is our history. Since 1987, we are stable and consistent growth of Transport Fluidyn Group, and it is fully owned by employees for long-term stability and technical orientation. We have scientific software development and solutions like optimization of industrial process by multiphysics and general CFD simulation. Then industrial, urban, and traffic impact assessment and solutions. We have our Panacea product is there, and some risk analysis problems also we are solving. We have more than 100 PhDs and masters skilled personals. We have global presence in as a technical centers in France and India, subsidiaries in US and UK, and also agents in China, Japan, Korea, and Thailand. So this is our total income in from the consultancy group, and around 12% from R&D in oil and gas and all this nuclear and all this. So here I want to explain a little about our software and services. For process design and optimization, we have also tools for CFD and multiphysics, conjugated heat transfer, FSI, what I told, fluid structure interaction, and MHD and electrochemistry, all this. Environment impact assessment, we have tool for urban air quality, health impact, industrial pollutions, water, air, odor, noise, all kind of pollutions are covered in it. Source appointment and leak detection in real time is also possible with our tool. Then quantitative risk assessment, risk analysis of industrial accident and toxic flame, fire explosion, dispersion of toxins, radioactive pollutants, all kind of solutions for VR tools. And last one is regarding ventilation and HVAC, regarding energy efficiency, and some filtration application is there. It is useful for hospitals, data centers, malls, parking, clean rooms, to clean rooms, etc. Ventilation optimization is also useful for energy saving, airflow in road, tunnels, mines, rail stations, etc. We are also describing our firm as R&D firm, and we have more than 20% of turnover from R&D. We have second GEP FTP Innovation Award in 2014, we got it, and we also nominated for Solvay Awards in 2006. We are also nominated to VNCI Innovation Trophy in 2015. Here it is some R&D projects we done since 2008. So I'm not covering in going detail in it right now. It's for reference only. This is our international reference, our global presence. Okay, you can see some Indian companies are also there. Is our reference Aditya Birla, HP, HL. We have also HL is using our customized software. Bark is also there. NPCIL, Reliance Industries also our good client. Some European references are also there. I am not going in details with it. I want to show you some key references what we have in India. In nuclear side, BARC, NPCIL, IGGAR, AERB, defense, DRDO. So many branches are there. Aerospace, ISRO, NL, ADA, really. Then chemical, oil and gas industries, we have Reliance, EL, ONGC, HPA. We are also in automotive and manufacturing unit. TVS, Gabriel, Renault are there who are using our tool, or we have also provided consultancy work to them. And many consultants are also there, like French ministry and from France, SIAAP. Like. So I want to introduce now about our expert speakers. We have Amita Tripathi. Actually, She did engineering graduation from NCSU USA and also PhD from École Centrale Paris. Had been also in Fluidyn, France from more than 20 years. So the next one is Krishna Prasad. He is a developer and manager of the environmental activity of Fluidyn India from more than 20 years. He is very keen on CFD code development with technical application. And Dr. Claude Sopran is also there. He did his engineering and PhD from most prestigious French engineering school, École Centrale Paris. And he has many researches with him. He did researches in academic world like Cambridge, UK, Ispra, Italy, CNRS, France, and before joining Fluidyn, France means more than 20 years ago. As all knows that we have today panel discussion at the end of webinar, and we have our as a guest moderator Dr. J.S. Sharma sir is there. He is a member expert and appraisal committee MOEF. He is presently working as president at Indian Association for Air Pollution Control (IAPC) Delhi branch. He gave notable contribution as deputy general manager at Oil and Natural Gas Corporation Limited (ONGC). He is also a member of National Editorial Advisory Board, member of Pariaksha and Enpro Society, which is non-profit and non-partisan professional NGO working for environmental protection since 1995. His interest lies in air pollution monitoring, prevention and control, meteorology, air quality modeling, monitoring and prediction, water pollution, and solid and hazardous waste management. Other our panel members are Dr. S.V. Misra is there. His advisory for ministry and specializes on major hazardous management. Then Mr. Subramanyam Nilkatan is there. Is ex-MD of Organic Peroxides Asia, ARKMA, and current director of Tirumala Chemicals Private Limited. He having a vast experience in handling process modeling and risk management. And Dr. Sanjeev Agrawal is there. He is the director of Amity Center for Air Pollution Control, Amity University, and he specializes in modeling of environmental impact due to industries and residential masses. And last one is Mr. Sharad Murukar is there. He is a process safety in BSFF and well experienced in managing process safety of hazardous chemicals and storage space Styrene. So, without wasting much time on it, I want to invite Dr. J.S. Sharma to share his experience and give little introduction about today's webinar. So, please, Sharma sir, are you there?
Thank you, Dr. Nirav.
Most welcome, sir.
I'm Dr. Sharma. My background is petroleum, and I was ex-group general manager and head environment in ONGC. The topic about Styrene leak, real-time dispersion forecast. Let me give some my thoughts and opening remarks. Can you hear me, everybody?
Yes, yes, it is audible, sir. We can hear you. You can.
So, just about this, since I worked in that area in Andhra Pradesh, that it was very clear from the central side as well as the state government side. The plant was ISO certified, but all system in place was failed on the 7th May. Nothing was available to rescue things, and it was poor maintenance. Then the refrigerator system of the Styrene tanks was not functional. Then the wind on that day was west to southwest, and it was expected about 3 to 7 tons of styrene was vapors were leaked. As per the certain prescribed units, styrene levels in the region were more than 2.5 parts per million. That means about 2,500 parts per million on the morning of the 8th May 2020, according to some media report published here. So it should be less than 5 parts per billion. Styrene was more than 800 ppm. That is how, on the 8th of May, that is how the people died. Some of the people died. It was also reported that the organic VOC monitoring equipment was not functioning there. The major failure was that it was not, their freezing system was not working at all. Since the plant was due to corona lockdown was not functional, only the limited maintenance was going on, they were in the process of restarting and restarting the plant. The proper protocols were not followed. This has been reported. The tank was having different layers. Styrene, and it was reported that some of the hydrocarbons were available at the top of the tank. So some vapors due to sunlight formed, and that's why how the pressure broken and walls were broken, and the vapors came out and they traveled to the surrounding areas. Styrene monomers were also mostly imported from the Korea or some other places, but the antidote to this treaty was not available. Within the plant, it was airlifted from some other places. So it took time to rescue the styrene. So in my opinion, it was totally a risk failure. The plant was so old, and the risk was done, must have done about 10 years, 15. So what I mean to say, the risk has to be done after every periodicity. And what happened during last 10 years, this plant has expanded its capacity to 5 times. For example, I can tell this has revised their capacity 5 to 6 times in last 10 years. For me, they were not having any clearance, and it was not appraised by anybody. You know, they can work with certain clearances from the state level, but the state level do not appraise from the safety point of view. This is not their part. So the risk has to be assessed from the center, which was not, the permission was not taken. But when they have taken, it was, when they have applied, then there were certain issues. So they have taken their application back. Now they have sued more to the Ministry of taking certain measures, and they are revising their application and all that. So this is the background of the accident which took place. It was a total failure of the risk. Nothing was available on the part of risk, and some corrosion was also there. They catalyzed the. So in this, when we points emerge, I will intervene. Now I invite Dr. Tripathi to come and make her presentation.
Okay, thank you. Thanks a lot, sir. So now I want to invite Amita Tripathi. He will start with some introduction and she will share some experience of Fluidyn in field of styrene leakage and storage and dispersion leakage. So Amita, are you there?
Yes, can you hear me?
Yes, it is audible. Please
Can
start.
you hear me?
Yes.
Thank you, Nirav. Thank you, Dr. Sharma. Can I share my screen?
Yes, sure.
Yeah, you can.
Okay, thank you.
Okay.
So can you see my screen?
It is not visible right now. Have you shared your screen? Yes, it is visible now. Yes.
Okay. So I'll just make a quick presentation to the colleagues who will follow up. This is just to show what we can do, or simulation can do, as far as the design and optimization of process is concerned, and specifically the case which we are focusing on today, which is the styrene storage process and how to store styrene. So thanks to the quick introduction done by Nirav, you know that we are dealing with optimization of industrial processes, which means a simulation of fluid dynamics, and so by fluid, of course, liquid and gas behavior, but combined with the temperature. So a combination of an interaction of the fluid with the thermal processes and the heat transfer, conduction, convection, and radiation, as well as the fluid structure interaction, which means deformation or displacement of the fluid, of the structure under the load, the pressure, or the temperature load carried by the fluid. So you have here a few examples, which I focused on more on tanks, about velocity vectors, velocity vectors simulated into tanks, temperature loads onto structure carried by the tanks, and displacement and deformation of structure. So now, if we're going into the specifics of styrene, styrene is one of the components that needs to be to be carefully the storage needs to be carefully designed, because it has to be maintained at a lower temperature, usually 15 to 20 degrees, because the flash point of styrene is at 31 degrees, and it means Celsius. I'm talking in Celsius here, sorry. So which means that at that point it vaporizes and it polymerizes, and it can of course become gaseous. So it's below that point it's liquid. It can become gaseous. It's toxic, and it can also have very exothermic reaction and lead to explosion. So every time there is a storage of styrene, there needs to be a refrigeration of the tank. So refrigeration needs to be here. And so the simulation can help investigate the process of refrigeration, and so when and how it should be refrigerated, or of course its failure, what happens in case of failure of refrigeration. So there is, depending on the type of process that are on site, there could be several ways to refrigerate. Of course, the refrigeration itself can be checked. The refrigeration can be shared between several tanks, depending on whether there is styrene in the tanks or not, and how many tanks of styrene are located on the site. Of course, it needs to be designed for various external conditions, including very hot weather, and it should be working whether the tank is empty, it's full, or it's being filled up. So there is one example we did some time ago for a major petrochemical company situated here in Europe. And so we did several types of investigation of process. The one I'm going to show here is a filling process. So the tank is empty. It's being filled up with styrene in 4 hours time duration. Then it's refrigerated for 24 hours, and then the refrigeration goes to another tank. So there is no refrigerator for the next 48 hours. So this is European condition. So it's less the extreme condition we have in Europe. Of course, are nowhere the extreme conditions there is in India. But so right there, the external condition that we had to focus on were 31 degrees during the day and 15 degrees during night, which is summer condition in France. But I realize and I appreciate that this is a kind of low temperature for India. But this is just to show an example. So if you can still see my screen, I'm sorry, my screen goes blank from time to time, but I'm trying to get it back on very quickly. You see here on the top view, the filling up, the simulation of the filling up of the tank. So the red part is styrene, the blue part is air, and into time, in 4 hours time, we are filling up the tank, not at about half the tank filled. So this is the mass fraction, liquid fraction, and gas fraction, and on the right side you can see the velocity vectors of the styrene coming in right at the beginning into the tank. And you see also the cycle of the outside temperature. So going from the outside tank, surface tank temperature, going from slightly above 35 degrees to slightly below 15 degrees during night and day. So if we check now what are the styrene temperature. So The first during the first day, the top view shows you the temperature inside the tank that are expected after the first day at 7 p.m. So the filling up has started, has been done, and now the refrigeration takes place. And we can see after second day at 7 p.m. and third day at 7 p.m. as well, the temperature inside the tank, which because of refrigeration and the alternance of day and night, it's actually not so bad. It stays cooler and below the 15 degrees Celsius temperature that we had expected and we wanted to have at the beginning of the simulation and the study. And you can see here the graphs at the bottom of my slide. You have here the red curve is the maximum temperature. So of course it's a local temperature, so it's a maximum temperature of the styrene. The mean temperature of the styrene inside the tank is in green, and the blue curve here is the minimum temperature of the styrene in the tank. And as we go along the 48 hours, everything gets mixed up, and so we tend towards a common temperature slightly slightly around 10 degrees Celsius. So in this present case, the design of the refrigeration of the tank actually worked, and we could tell our clients, so the petrochemical company, that what they have in store and designed for the refrigeration was actually working in that present case, and did not lead to a temperature going above the set and the target temperature. So this is very, very quickly what we can do for a design process. I'll hand it over now to Krishna Prasad to explain to you what happens when this is not carefully monitored and the process has not been carefully designed beforehand. Thank you.
Thanks, Amita. Now we will hand over to Krishna Prasad. He will show you some live example about real-time simulation and real-time monitoring system. So please, Krishna Prasad, are you there?
Yeah, Nirav.
Yes. Okay. So please.
I'm audible, right?
Yes. Yes. It is audible.
Thanks.
Yes.
Yeah. Yeah. Thank you, Nirav. Thank you, Dr. Sharma. And I would like to, with your permission, I would like to share my screen to begin with the presentation.
Please share your screen.
Yeah. Okay. So I'll be talking about what happens when some toxic material gets released as vapor or aerosol, and without going much deep into technical overall concepts of what is going to be the criteria for the modeling, etc. The things that we need to take care of while selecting any modeling, any model. So let me just give a brief introduction on risk, managing risk overall, not only with respect to dispersion. As a routine analysis, usually we do whenever we take tackle risk. It will be either dispersion of accidental release and dispersion of hazardous materials, or it will be a fire, various type of fire, jet or pool fire, etc. And their radiation impact and explosion and their pressure wave effects. And most of the time, which are quite rarely that are being done, is the integrated approach to risk modeling, which are mainly required mainly for design. As an example, I have listed some aspects here. That is explosion or fire modeling with structural damage, which we usually don't do, even fire modeling also. The effect of thermal radiation on structure failure. And process modeling, my colleague Dr. Amita just briefed what happens when the process go out of control, and there'll be a loss of material from the containment and subsequent dispersion of the same in the atmosphere. Then optimal sensor mapping. Of course, sensor mapping is being done quite as a routine nowadays with using several tools. But how to do it optimally? By taking care of all the aspects that are supposed to be considered. I mean, it is multi-pronged approach in detector mapping. In any plant which is considered to be handling such materials. And source identification from sensors. Of course, the functionality of sensors doesn't stop at mere detection of any leakage. It also can be used as further in analysis of identifying the source and quantifying, etc., which might which will be briefed by my colleague Dr. Cloud later. And that too in real time, in fact, whenever the accident happens in real time, because these sensors will be placed in such a manner that, in such a configuration that any such leakage can be quickly picked up, and the suitable alarm can be given, as well as it can give much more information on the leakage, and the decision-making processes can be done using such sensors. How can we completely utilize the functionality of sensors, probably? And then real-time forecasting of gas dispersion. Whenever there is an accident and sensors pick up, and we'll identify the source. Usually in such instances, we'll not be the place of leakage is not approachable, it's not accessible. So we'll have to do everything in remote. So some system which should be in place which can give us some idea about where the leakage has happened, and how far the impact area is going to be by sitting at one place, in fact. Now, risk management when it comes to gas dispersion, hazardous gas dispersion, it is not as simple as what it appeared to be. In fact, there are many minute things that may have to be taken care during the modeling aspects, in fact. It begins from the release itself. The toxic flammable gas release, it happens under different conditions, mostly abnormal. That is failure of something, failure of equipment, failure of the systems, etc. So it can be of high and low density, high or low density release, which has its own behavior while dispersion, during dispersion, and it can have high or low temperature also. So the local turbulence that is caused by the release itself will be of prominence here. And high velocity jet, that also actually is prominent. Often it is associated with or without phase change. That is, initially it will come out as aerosols or droplets, then it may get evaporated, or it may condense also in some other instances whenever for example, the cooling tower, the nuclear releases from the cooling tower, in fact. And often it is associated with the transient phenomena. That is transient release also. That is whenever accident release happens, it is not constant. It is not uniformly releasing whatever whatever inventory is there. So there'll be a time varying releases, which needs to be duly considered for the impact or risk assessment, along with combined with the transient nature of the weather. In fact, over the period of release, the weather may not be constant. Some of the other challenging aspects here are in jet releases. That means whenever pressurized gas, liquefied gas or pressurized gas comes out, it will come out as a jet, and the jet direction against wind direction. So how it is going to behave when it comes out. So this initial cloud formation is very much important to be studied also. And when I said initial cloud formation, it also depends on local site occupancy. That is, what is there around the release point, whether it is a free atmosphere or it is congested with a lot of buildings around, etc., or a lot of facilities around. And also subsequently, when it moves out of the site, then what are the complexities that it has to face during dispersion. And in the offsite features, we know that the topography is highly non-homogenic. That means the land coverage. For example, out of the site, out of the industrial site, it can be, it can be a there can be a green belt area, and also there'll be a village or farmlands, etc. So all of them are quite quite different in imparting their own effects on the dispersion. In fact, now when I say the minute aspects that are to be considered during dispersion, it starts from release, of course, what type of release it is, and how the release has initiated, what is the configuration of the source. One of them is this one. As we all know, I mean, of course, these are the things that we already know about, but during modeling, these aspects are being not being keenly or considered in detail, in fact. So release due to rupture of pipeline or vessels, aging of equipments, that is normal operating conditions, and many process control failures, or even sometimes what happened in Vizag, actually, it is also failure of some safety equipments. So the normal operating conditions will not be there. It will be abnormal. So why I'm saying this is in both the conditions the release could be different. Under normal operating conditions, the material may get released as a gas alone, or maybe liquid alone, or under abnormal conditions it may come out as some other phase, or with some other force, in fact. And secondly, the release due to failure of gas treatment systems. In fact, whenever some releases happens, immediately there will be a vacuum system which collects such toxic gases, and there will be a system which treats it. But if such system itself gets failed, then what is going to be the release? This release is completely different from what is happening at a pressurized release. So here the concentration as well as the behavior of the gas that is coming out will be completely different, which is to be taken care while modeling. And thirdly, the third instance is toxic byproducts from fire accidents. Of course, whenever a material, as it is, when it gets evaporated or when it gets released, may not be that harmful, but when it gets burnt due to fire, then it will be highly toxic, and the smoke or byproducts, fire byproducts that come out will have high energy, high temperature, and it will get lofted onto the atmosphere and then go and settle somewhere else. And this fire also happens over a larger region, may also happen over a larger region. So you cannot treat it as coming as a source coming from a point or a small region itself. Then evaporation from the pool. It is quite different from what we have seen previously. So this is the evaporation. This is highly transient, as in when the energy is available or heat energy is available, the evaporation rate also gets changed, and it is just entering without much force, of course. So all these type of release types are very much essential to be captured when we do the modeling of dispersion. The second and third, of course, major aspect of dispersion modeling is weather and topography. We can consider them separately also, and mostly they behave together, in fact. So weather itself, when we consider this image, so I'll just try to present you one scenario where highly non-homogeneous path for the plume, where it has to encounter some a township, or it has to pass through some forest region or hilly region, etc., or water bodies, etc. So whenever wind enters a region, so it will enter in different layers. We know that there will be some profiling, some stratification of wind in the vertical direction. It will not be uniform all over in the vertical direction. So with that particular stratification itself, in the bottom layer, wherever human activities are prevalent, so we can see that based on our activities and based on the land coverage that plume has to travel through, will have its own influence on the plume dispersion and plume path also, plume propagation. So okay, so once we consider this, if we go, this is on my larger scale. For example, over a region of say 5 to 10 kilometers, we'll encounter such phenomena. Then coming to quite a little bit local local environment, we see that there'll be buildings, and in between the buildings there'll be the circulation pattern, and also there'll be say for some vegetations, etc., over which when the wind passes through, there'll be high range of turbulence or high variations in the wind, both in direction and its velocity. Especially in this particular layer, we can see that the mixing layer completely changes from meter to meter, or even over 10 meters in this region for this particular, for example, local scale, micro scale modeling. Then when we come to very highly local scale, that is micro scale modeling, we know that whenever wind passes through two different buildings, two adjacent buildings placed quite near to each other, the person who is staying at different locations, he'll have he may receive concentration due to several reasons. In fact, there may be building downwash also, which which captures, and there'll be eddies which can carry the complete plume into the gap of the building, the space between the buildings. And also there can be some air handling units that are present in the adjacent buildings, or window itself, for example, open window, which can also play an important role in supplying this hazardous gas into the occupants. So they are all actually interactive. In fact, topography and weather. Because of the topography, there will be local variation of the weather, and because of the weather, the topography, of course, itself will be playing an important role in modulating the weather locally. Now, how we have been modeling all these aspects all these days? In fact, we have a simple model here. I'm not going through the details of this particular equation. Of course, you may be aware of that. This Gaussian model, which is 1D or 2D, whatever we call it as. So we have been using this model for all the days, and it is quite handy in nature.
Mr. Krishna Prasad, your voice is not clear. You check with mic. Mr. Krishna Prasad, your voice is not coming. You just check with your mic. Your mic may be turned off.
Hello, my
Muted.
hello. Is it okay now?
Unmuted.
Yes, it is audible now. Continue this.
How about now?
Yes, it is audible now, sir. Please continue with it. Yes.
Okay, fine. Okay. So I was just coming to this particular equation, which we are well aware of, quite familiar with. So this is Gaussian model. So there are many assumptions in making this model simpler than what it was used to be earlier. In fact, flat terrain with homogeneous roughness, but that means the complete domain, if you consider it as this box, then inside the box, the terrain is completely flat, and it doesn't contain any complexities. Then this has been derived by assuming point source actually, and it is always when we see the nature of this equation, it is only applicable for wind speed about 2-3 meters per second. We see that the velocity comes in the denominator. So if velocity is, for example, it approaches 0, then this equation fails. Then reliable. This model is reliable only for the regions beyond 200-300 meters from the source. So any model which makes use of this particular equation or any other form of this equation may not be very much useful in estimating, especially the risk, because risk, when we talk about, we don't talk about kilometers of distance. It will be mostly near the site or near the release point, at the most. That's it. So then, what is the alternative? There are some, of course, deterministic models which can take care of this by duly taking into account the aspects that we have considered, that are supposed to be considered in the dispersion modeling. In fact, the first is the topography, as we have seen, site data. Usually, when I present it as a step in a deterministic modeling. Actually, what we need to do is the complete physical description of the site that we need to model are to be taken into account. When I say physical description, means say altitude, terrain undulations, or within the site there may be a lot of buildings, etc. There may be several facilities around the site in terms of urban region, or there may be vegetation area, etc. Then once we capture all the details of the site, then what is called as some meshing is being done. That means we completely discretize the complete domain of our site into small control volumes. There is small boxes. It is not single box, so millions of boxes will be created. Then what we do is we'll study the wind flow, how the wind gets modified when it flows over the region of interest, duly taking into account the features. For example, if I take an example, if I take the example of Vizag, then outside the plant there are a lot of it's quite outskirts to the city, so there are city buildings adjacent to the plant and the buildings within the plant also. So how it gets modulated, we have to note that this is the wind which carries the dispersion, of course, the toxic material downwind. Then once we establish the flow field in the region, then we subsequently we proceed towards dispersing the plume under such wind conditions. Now in broad, when I discuss, probably so it's the overall topography. When we talk about the dispersion over a large region, for example over 2-3 kilometers also, then the complete topographical nature of the region can be considered. What we see is a highly mountainous region, or is it a forest region, or it is a plain land, or it's an urban region, etc., can be captured in the model. So what we call as the CAD model, all these features and the model shall be having the capabilities to consider all these things as CAD objects. In fact, objects, the representative objects. So similarly, close to the site, when we come, as I said, whatever happens close to the release point should not be neglected. That is also very much important in estimating the initial cloud. So initial dilution or initial accumulation of toxic material is also very much important. That can be done by properly considering the site features, what are the facilities that are within the site. So what we call as obstacles to the flow or obstacles to the dispersion also. Then it is aptly meshed. The model should be having the capability to consider them properly, and the proper mesh has to be created. We can see that based on the different configuration, site configuration, the mesh, different type of mesh are being generated here. That the model usually will be having its own capability to do that. In fact, built-in capability. Then
Yes, sir.
it is
Yes, sir, I'm interpreting. Please, actually, we have some time limitation, so if possible to make it for as soon as possible.
Yes. Yeah, I'm closing it. I'm closing it another 2-3 slides. Yes.
Okay. It's okay.
Yes. Yeah. So then what we'll be doing is once we have captured all the 3D features of the site, its physical topography and all the 3D physical features, then we will be carrying out the flow field analysis, that is wind flow, using CFD, we can see that in close site space in area, what is the influence of the wind, influence of the features on the wind, for example, how the wind flows around the buildings, etc. And on a larger scale, we can see that how the wind gets modified in the presence of some undulations. So we can see the in vertical section, we can see how the vertical layers, the flow layers gets changed from point to point. Then finally we'll carry out the dispersion, in fact, over the wind field established. This is how it looks like in different instances. In fact, whatever you see here is dispersion over a highly undulated region. Here we can see the dispersion over a highly congested area, which is which has a lot of buildings around, etc., within the plant. So here there are a couple of animation which which are self-explanatory whenever it comes to dispersion of cloud. So we can see that this cloud doesn't have any fixed shape as we assume in some other 2D models or contemporary models, in fact simpler models. So it will gain its own shape whenever it encounters some some disturbance in its downwind direction. We can see that after some time, in this case especially, the concentration gets built up because of the the plume that gets lofted in the beginning will come down and gets recirculated inside here. Couple of other cases here where the cloud movement as well as transport in the downwind direction. This is ideal H cloud, in fact, of some toxic chemicals. Now, of course, this sensor mapping, mostly my colleague will be, Dr. Claude will be presenting it. Anyway, let me give some brief introduction. Whenever we do sensor mapping, it's the same aspects whatever we have considered in dispersion, they have to be taken into account, in fact, because the dispersion, the sensors are placed to capture the dispersed gas. So how the gas disperses is very much important to model in the beginning, in fact. So we first develop the CAD model, and then we identify all the sources, the probable sources, and establish the flow field. You can see that the vertical direction, how the wind flow gets modulated over this region, and how the dispersion also gets modified over that. So what we do is we formulate clouds from all the possible sources and superimpose them in the realistic conditions, that is by duly taking into account all the obstacles and the wind modulations, etc. The subsequent cloud formed due to any eventual leakage will be identified, and it's mapped, and the overall map of all the leakages will be used for the sensor mapping, in fact, to identify the locations of non-coverage. For example, if some region is not covered or some source is not covered, in fact. So how to change the position of the detectors so that a single detector can serve more than one or more than multiple leakages, in fact. So with this, I'll be concluding, and thank you for your time and patient hearing.
Thanks a lot, Kapil. Now I want to invite Mr. Claude Sopran. He will discuss and share his experience about inverse modeling and risk detection and real-time forecast. So please, Mr. Claude Sopran, are you there?
Yeah, can you hear me?
Yes.
Yes.
Okay, good. So I'll share this screen. So I have 70 slides. So it should be okay for the presentation. I will focus, as explained,
Okay, Dr. Cloud.
Your voice.
You can proceed, Dr. Cloud.
Claude, sir, your voice is not audible, I think. Mr. Cloud sir, are you there?
Amita?
Yes, maybe I'll take over until the sound problem from Claude is fixed. I don't know. We have been from the French side. We have had problems with sound since this morning. I don't know what's going on, but I'm sorry about that. So Claude, I don't know if you can hear me. If you can, then you can maybe put your presentation on, and I will start.
I thought you were audible, no problems. Only Claude is not audible.
Yeah, I had problems earlier, so I know that there was a problem with France. But anyway, maybe I can share my screen, and Claude can pick up when he can.
Okay.
Okay. So Claude, can you change a slide?
Can you put?
Thanks. So I'll just to explain what we'll present here. We will present the real time. So how, in case of the unfolding of an accidental event, how we can take measures to know when and where the leak is happening and how it will unfold. And then I know there was questions about this during the presentation. We will show also a quick simulation that Claude did regarding the VISAG accident and what we could make of the information that we could get and how we could model the unfolding of the accident. So this will come up just after this presentation. I mean, during this presentation, sorry. So Claude actually did the work, so I'll supplement for him until he gets the audio back. So just to explain what we did, this was something that we have done initially for Army, but now has been deployed for all industrial cases, where we have a monitoring system. Can you share my screen, please?
Yes.
Thank you. Thanks. This is a monitoring system to monitor in real time accidents that may happen on site. To do that, we have you have seen how Krishna Prasad explained how we needed to take into account the 3D setup, so buildings, topography, and also the network with sensors. And to do this, to go to a reconstruction of the accident, of the unfolding accident, we need first to know where the source happens, depending. Maybe I'll go back. Depending on the measurements and the information that is being located that is being given by the network of sensors. From that information, go back in inverse modeling, in inverse time. So go back in time to see where the source is coming from and how much of the material is being released, and then do a fast forward simulation to see what would happen in the next 15, 30, 45 minutes to know actually what and where what to protect and where to protect people, where the cloud will go. So not divide your efforts and really go to where it is needed. So I'll probably go very quickly over this part because we are a bit short in time. But what happens is that you can see here what the software will actually how the software will actually look like. So what you see here is a visibility function. Visibility is what the sensor network is actually seeing. So what is visible by the sensor network. So when it's red here, that's where it's very well seen by the sensor. So an emission source will be very well seen. and where is green or blue, it's where it will be less seen, and where is there's no color, nothing, it's invisible. An emission here would be invisible by the sensor network with a specific wind direction. So of course the sensors are right at the middle of the red spot, because if the emission occurs at the location itself of the sensor, of course it can very well see it. So this is the visibility of the network. And then when a simulation on the right side is when an emission occurs, a dispersion occurs, then you will see that if you combine this visibility map with the actual reading of each sensor, you will see that all the sensor will see more or less the actual emission, and where all the sensor will have the highest reading, so where is the red point here, that's where the emission is actually occurring. So this helps, this gives you the information of where the emission is coming from. So this helps for a quicker decision making to stop the emission leakage. So we have done a few cases with trying out with two sources of emission starting at the same point. So you can see here on the right side that we can locate the two sources of emission. That's the black dots that you can see on the map. Or if the emission is outside the visibility map, you can see that the red zone is going towards the actual source. So it's a very robust way of dealing determining where is the source. So you see here doing it in real time, so including and integrating measurements actually given by the measurements, the actual measurements, the real data, and it's being integrated in real time into the software, and you can see the visibility function changing. So maybe due to time constraints and problems, I'll just jump to this simulation when you can see in real time the emission source is located here, and you see in real time that with the measurements arriving at the sensor network, the sensor goes backwards and give in a very fast, where in a few seconds where the source is expected to be. So that's where the black patch occurs here, or red patch occurs.
Amita, Dr. Cloud's voice is now okay. It is audible.
Oh, okay, good.
So we can hand over to him.
Okay.
Yes, sorry for this trouble with connection. Thanks, Amita, for catching up. Just a few words about the conclusions. The real-time systems we deploy is made of several bits. The first one is the optimal sensors. We use this visibility function. The second one is to localize instantaneously the sources and intensity as soon as a set of measurements is coming from the sensors network. So if a sensor has a sensitivity which is good enough and fast enough, we can have a few seconds to locate the sources. So in the control room, when the system is deployed, basically the operator can see immediately a source map going on and can identify the location and operate mitigations. The last thing is that the system is compliant with background sources. And in case, for example, sensors is failing in producing wrong values, unique sensors, the fact that the data collected by the other sensors is interpreted simultaneously, you can identify which sensor is failing and giving false alarms. And multiple sources can also be identified. So the requirements for this system is not so long, it's not so important. In fact, it needs good sensors. The numbers and distribution can be optimized with the applications, with the technology. And of course, it needs some preparation offline beforehand during the deployment phases with the calculations and quite large databases to be prepared beforehand. So so can I share my screen, or Amita, can you just keep the slide for me? Okay, thanks very much. The second part of this talk is okay. So I'm going back on mine. Yeah. So I'm going back on mine just to explain what we did on VSAC cases. Can you see my screen now?
Yes, yes, it is visible. Can you change it to more to present, please? Okay.
Okay. So it's a few slides explaining a very first demo cases of the technology that can be deployed for real accidents. So take it as a demonstration cases because this case we use very crude data collected mainly from newspapers and first guesses. So you have the list of newspapers that we've been using. And we also collected on the internet specifically to build up the 3D models, information like location of a plant, the aerial views from Google Earth and from road maps. We also collected GIS data. GIS data is quite useful because it produces the land cover, some of the buildings. You'll see later that for this plant in Visag, we had to use the aerial view to build the buildings. And also we have direct access, free access to USGS terrain information with quite a good resolution, horizontal. So we also use the information, crude information from the wind condition that was occurring from noon to 15 p.m. on May 17th. And we also noticed from the newspaper that some of the villages has been impacted nearby the place. So next, so the very first analysis from the newspaper is based on photographs. So we see for the tank storage of one of the tank storage of the Styrene, the location of the plumes and likely the origin of the gas emissions. So this has been crudely used to locate the source on the plant. But before this, we had to build a setup. So you can see the typical setup that has been built for Visag with terrain elevations in red, road networks, and a zoom with details informations from the aerial views for the plant itself on the left-hand side. And on the right-hand side, you see in the central part the design of the plant with the buildings, the two main tanks, which are located in the center, and in the boundary, the elevation curves and terrain elevations. So we had also to guess possible scenarios. So we've been using thermophysical data for the terrain. For the dispersion, of course, we need the gas density and molar mass because it's a heavy gas at normal temperature. And we also use the fact that when reaching 145 degrees, which has been reported in the newspapers at the maximum temperature in the reservoir, the pressure can build up to 1 bar, the overpressure. So it means that within the tank, it could have been a partial pressure for Styrene. The total pressure could be 2 bars. So we use this estimate and very rough arbitrary sizing of the valves to estimate a flow rate in kg per second and the process function of the gas at 30 degrees. So the source is located somewhere arbitrarily near one tank at ground level, even if afterward this may need to be updated on a post-accident analysis. Because we expect heavy gas behavior with limited mixing with weak winds, nighttime winds and early morning winds were quite weak. We expect a creeping behavior for the cloud And we also need for the solution to solve Navier-Stokes equation with temperature and gravity model. I'm not getting into too much detail on the model itself because Krishna Prasad already explained. So the very first output of this case is what you can see here, the top view on the plant with the two reservoirs, the flow which is developing. It's weak winds, so you see the scale. It's only 1 meter per second maximum at ground level. And in this wind, you can see how it's evolving. So you have this is I don't know if it's animated kind of plot sideways with the buildings, and in between the building, you see how the flow is evolving in time, changing in the lee of the plant. So based on these calculations that has been performed for the very first transient scenarios, 21 minutes, we dispersed the cloud from the possible initial origin of the gas with the first gas estimate of rates. So you see the cloud evolving for the 21 first minutes, and the threshold color shading is basically taken as 1×10⁻⁴ as a mass fraction of the gas, which means slightly less, 1 order of magnitude 10 times less than the expected IDLH effects on people. Of course, those data needs to be refined with a real estimate of the cloud rates, but it gives you the paths of the cloud evolving on time for the very first minutes. So you see that quite very quickly for this threshold, the cloud is engulfing a large part of the plant, and out of limit of properties gases is producing later on. Of course, more you accumulate in time for more than 20 minutes, maybe hours, the release, the larger will be the expansion of the gas. Now, if you look at the 3D view of this cloud, for another given threshold, which is 2×10⁻³ mass fraction for the Styrene gas, you can see how it expands in 3D. So you see the effects of the buildings. You see how it changes in time due to wind variations. And for the very first 20 minutes, when the wind is increasing, the dispersion may become better, and so on. So these are the very first illustration and demo cases of the BISAC accident, where based on very simple information, GIS data, aerial views, and basic information on the very first analysis of the scenarios, we can produce 3D models and analysis. Of course, for the LG plant, we have no access to the sensors data if there were any, and thereby we cannot use the collected data before the ignition, the startup, the kickoff of the leak to see whether we would have been able to relocate the sources and to produce an early warning alarm based on the inverse modeling and sensors data analysis. So if you have a question on this, I can close now. I think that somehow we are quite late now. So
Yeah.
Yes,
Yeah,
sir.
go ahead.
Yes, thanks a lot, Dr. Cloud. So now we have time for a panel discussion, and I want to invite Dr. Jayesh Sharma to give green signal to webinar panel discussion with V.S. Misra ji is there, I think, and Subramanyam sir, Sanjeev Agarwal sir, and Sarath Murukka sir. So, Misra sir, are you there?
Subramanyam sir, this is Sharma here.
Hello. Dr. B.S. Misra sir, are you there?
Mr. sir not there, and Sharan Mundra is also not there.
Okay, Sanjeev Agarwal sir is there, I think. Hi, sir.
Dr. Abraham is there?
Mr. Subramaniam, sir. Yes, he's
Yes.
also there. So,
Yeah.
please, sir, Sharma, sir, I am handovering to you now. Please start with the panel
Yes, yes.
discussion. And
So, meanwhile, when the Dr. Agarwal and other panelists join, see please connecting. So, we start with the Subramaniam, this is Sharma here, and I just wanted to know, they have presented in the background their software, the sensor mapping, process safety control, the 3D of various models. I just want to know when the several industrial complexes are there, not isolated plant. In several industrial complexes, how to do this modeling risk. Suppose we take an example of the Surat. There is IEC, there is ONGC, there is Reliance, and all lines are connected. And these plants have come over a period of time. But now, when they came up, there was no population, no full urban area is there, fully developed, and this when they carried out maybe 10 years back, they were renewed. So if any accident take place, in terms of leakage, like few years back, there was a leakage in IOC, Hanira also, there was some fire. So, this kind of things, how this kind of risk analysis 3D model will be helpful.
I think Amita should, probably, Anita or Krishna Prasad should answer this question. My impression was that this is a model live current based on the current, probably the use of Google Maps, current meteorological conditions, and it is something which is very dynamic. Am I correct? Some of the experts can answer that.
And the surveillance, you can share your experience based on process safety and this kind of leak.
Amita or Claude?
I'm sorry, I couldn't hear quite distinctively the question. Could you?
The question about the large industrial area. There are multiple sources, a very, very large area. How we can model in that situation?
Is the question about how do we model it with simulation, or how do we discriminate with sensor? Because modeling with simulation, it's of course takes a bit more time and more resources, but it's not that difficult. We have been dealing with industrial sites that are a few kilometers in length, in France, in Europe, in Japan, and so this is so it's of course more complex, more geometry, but it's completely feasible now with the current computer possibilities. And